So this is merely a proof that we've already made use of. So let's take the material time derivative of a volume integral, and for the purposes of this derivation, we'll consider that this is the material time derivative of the volume integral of rho times a quantity phi, and phi is some sort of density of another quantity, capital Phi. So where little phi is the amount of the quantity big phi per unit mass. This material derivative of the integral therefore represents the rate of change of the amount of capital Phi, which is associated with the particles that instantaneously occupy the region R at time t. Remember, it's a material derivative, so it's a rate of change as seen by the material particles. Hence, we can write an expression for the rate of increase of the amount of capital Phi within the fixed spatial region R as being the sum of the rate of increase of Phi associated with the particles instantaneously within R, so that's the part that comes from the material derivative, together with the net rate of influx of Phi into R across the boundary of Rs. So mathematically, this statement above would be the partial derivative of little phi times rho with respect to time integrated over the volume equals the material derivative of the volume integral of phi times rho with respect to volume minus the surface integral over S of phi times rho times n the outward normal dotted with phi the velocity vector integrated with respect to the surface. And remember, the minus sign here for an influx is because the n is an outward normal, and so this term here would represent an outflux, an outward flux. Applying then the divergence theorem and rearranging this expression, we'll obtain that the material time derivative of the volume integral over R of phi times rho with respect to V is equal to the volume integral over R of the derivative del phi rho del t plus the divergence of phi by rho by V integrated over the volume. Now, in the special case when phi is equal to 1, this integral is the mass within R, and conservation of mass requires that the material derivative of this integral is 0. Hence, when phi is equal to 1, the integral on the right-hand side must be 0 for all regions R, and thus the integral, the integrand itself, must be 0. For phi in general, we can expand the integrand on the right-hand side. We'll get phi times del rho del t plus the divergence of rho v plus rho times del phi del t plus v dot grad phi. Now observe that this term is actually 0 because this is the continuity equation. And this term here is the material derivative of phi by the definition of the material derivative. Therefore, putting all this together, we can write that the material time derivative, big D dt, of the volume integral over R of phi times rho dv is equal to the triple integral of rho times d phi dt with respect to volume. So this is the substitution that I was using. You can see it didn't require that the density rho is constant with respect to time. Rather, this is a simplification that came about from the definition of the material derivative and the continuity equation. I don't think it's important to memorize this result. I'm just showing you this so that you appreciate that there was no simplification or error or approximation in the derivations of the conservation laws that we derive for conservation of linear and angular momentum.